Am I audible? Yes. Good afternoon, everyone. This is our 17th lecture of the Cloud Physics and Dynamics lecture series. Today we have Professor Paul Field from UK Met Office and University of Leeds. Am I audible? Yes. Good afternoon, everyone. This is our 17th lecture of the Cloud Physics and Dynamics lecture series. Today we have sorry about that. So today we have Professor Paul Field, who holds a joint deliver our lecture, who holds a joint position with the UK Met Office and the University of Leeds. Paul studies the processes within clouds on microscopic scales which control the formation of rain and other precipitation to the scales of organized weather systems. He makes use of field observations, especially from the FARM aircraft, which is the Facility for Airborne Atmospheric Measurements research aircraft, to develop new theoretical ideas about cloud processes and dynamics. As part of the Dynamics and Cloud Research Group at Leeds, he collaborates closely with those studying cloud physics and large-scale weather systems. His group at Met Office is using these results to develop the next generation of weather and climate prediction systems. Implementation and testing of a double moment cloud physics scheme he will be discussing today. That name is KAZIM, which he is intending to use in Met Office unified model. And results will be shown for the performance in the tropics as well as over UK. So the improvements will be highlighted as well as the discussion about what challenges remain will be discussed by him. So let us welcome Dr. Paul to this lecture series, and we are very much honored to have you. And Paul, please. Thank you.
Okay, can you hear me okay?
Yeah, I can hear you.
Excellent. Okay, well, thanks for inviting me, and it's good to be here. So I'm going to talk about our new double moment microphysics in the unified model. And first of all, I need to thank these people you can see down here. So Ben and Adrian implemented the double moment scheme into the LES first, and then we've been exploring its ability in different regimes and getting it over the last few hurdles and implementing it in the unified model, which I know is used in India for things like the Delhi model. So hopefully that's of some interest here as well. See if I can. Yep. So microphysics schemes. So a cloud microphysics scheme is mainly used for doing things like working out the precipitation amounts you get, either rain, snow, graupel, things like latent heating and cooling, which then feedbacks on the dynamics and then can then generate or create more clouds. As the radiative properties of clouds, again, that can change the heating in the atmosphere and eventually change the dynamics in the clouds. And the other thing we're interested in is how cloud fields act as a sink of aerosol. Won't say so much about that, but that was one of the motivations for our new microphysics is to link it up with the aerosol. So, well, first of all, so whenever you predict things like rain or the amount of rain falling out of a grid box, you need to know something about, say, the fall speed as a function of size. You also need to know things like how droplets can collide and make bigger droplets and evolve within the cloud like that. And so as you can do that on a size by or particle by particle basis, but then you have to integrate over all of the droplets and all of the sizes of droplets to get a bulk measure of a rate such as sedimentation or flux out of a cloud box. And so to do that, you have to know about how the numbers of particles are distributed as a function of size. And so typically you use this sort of expression here, so the gamma type distribution. And so you've got a number concentration, or this has been normalized number concentration as a function of size. And these are just using two different values for this shape factor here, or dispersion of the distribution. And so for each size, you'd integrate over some property, say fall speed and mass, and then you could get the sedimentation flux. So typically, what people have is single moments. That means the model is only predicting the mass of the particles, but then you have to assume something about the shape of the size distribution in order to get the number concentration. So you might assume some forms or diagnostics for these n naught and mu in there. Then the next one is double moment. So now you're not only predicting the mass, you're also predicting the number concentrations of particles. And again, you have to assume something for the shape. But you can go a bit further. So triple moment. So one way to do a triple moment is you have is mass, number, and then another one. For example, you could take radar reflectivity. And then if you predict all three of those, that would tell you how this shape parameter changes as well. So, but those are simplify or bulk schemes that have relatively few, although you can see you've doubled the number of prognostics to go from this one to this one. But you can have more complex is to go to a bin type scheme. So now we've broken up the whole of this analytic curve into lots of bins of different sizes, and they can have mass information, or they can have mass and number information, and you evolve them by working out the flux of mass and number between bins. And you can see straight away that there's many more numbers you have to predict or remember. So that increases the cost by 10 or up to 100 times, however many bins you have, relative to those simpler, cheaper bulk schemes. And it's led people to use these because they're potentially more accurate, to use them to generate or to tune bulk schemes or generate parameterizations for the bulk schemes. And these are now being challenged or attempted to be replaced by these superdroplet approaches. I think you've got a lecture coming up on this. And so now you've got, instead of your bins, you populate each bin with droplets, say, and then in a bin scheme, you'd move a box up in the atmosphere, and you'd work out how the bins got populated as particles grew. Whereas in the superdroplet approach, they'd follow Lagrangian trajectories, and you'd represent integrate the growth or evolution of each droplet along its own trajectory. So potentially this sort of superdroplet approach can be more accurate, but we won't be covering that. That was just to show there's a whole range of spectrum of complexities that can be represented with cloud microphysics schemes. So this is my very simple picture of how things have gone in operational NWP. So in research, things have been a bit earlier, but by maybe 10 or 20 years. But in operational NWP, in the 60s, the first very simple, two-level model, models would have no clouds. Then in the 70s, we started to see very simple diagnostic rain. And then it wasn't until the 80s where we started to prognose total water, so the condensed plus vapor added together, and then you condense some out. But the ice was still treated as a temperature-dependent function. So depending on where you were in the atmosphere, would just tell you how much of that condensed water was ice. And then in the 90s, we started to see, coming to operational use, liquid and ice prognose separately. And then in the 2010s here, Canada started introducing both this double moment, both number and mass prognose for all the species. And I think maybe Canada might be even just about or have introduced a third moment into their operational setup. But anyway, we're not that advanced here. We're just looking at the number and mass prognostics. This is where we are at the moment. So this is our scheme, KAZIM. So if you look in the bottom left here, it stands for Cloud Aerosol Interacting Microphysics. And so our old microphysics single moment had cloud droplets, rain, snow, and growlpool. And now we've added cloud ice, so small ice falls very slowly, represents smaller particles. And before we used to just have mass represented, but now we also represent number. So we've gone from 4 prognostics to 10 prognostics now. And in fact, there's another 2 we have to do because we have to have cloud fraction also has to be prognostic for doing the activation. And then the thing that we won't really get into much, but KAZIM can be coupled to represent to the aerosol to represent either CCN and or isonucleating particles. And so it was designed to fit directly to the UKCA mode, which is the Met Office's representation of chemistry and aerosol that it uses. The aerosol's a double moment aerosol as well. But it also can work with Merck and Arcle. Merck, I think you use something similar in the Delhi model here. It's a single moment, so it's just a prognostic mass only aerosol, which is advected around the domain. Arcle is again single moment, but it's just a climatology. So we use that whenever we haven't got single moment emissions inventories. So if you're a aficionado, this or if you're not, or we don't worry too much, you can not worry too much about this slide. But the is a semi-Lagrangian advection scheme, and so what that means, so we've got a start of the time step here and the end over here, and the advection occurs over in the middle here, and it's actually iterative, although in the end, in practice, it just uses 2 iterations. So KAZIM goes in this bit at the beginning where radiation does its thing, and KAZIM works out all its process rates. Then those are passed to advection, and that works out where the trajectories go. But along those trajectories, you may have cooling of air, so and mixing caused by the boundary layer, and so condensation can occur here, which leads to latent heating, and so that has to be fed back into the advection to recalculate the new locations of the endpoints of the trajectories, and so you've got this separation of the cloud microphysics here and the condensation that goes on here. And then because the condensation occurs here, we have to have the activation at the end as well. So the whole of clouds is spread throughout our time step, and it's not just a function of the cloud microphysics. It also involves the boundary layer scheme, or if you go to global model, it's even the convection scheme, so mixing, any scheme that does the mixing of the water. And also we've got our new bimodal cloud fraction scheme that uses subgrid turbulence information and also hydrometer information to work out how much to condense. I've just got a few cartoons to demonstrate that. So this is just a plot of frequency histogram of supersaturation. So this is if you add all the condensed water and the vapor together and then work out the supersaturation. And so in the subgrid, you assume it's Gaussian with some width, and then everything that's above water saturation would condense out. But if you add ice to a grid box or more ice, what that tends to do is it acts as a sink of the vapor, and so it reduces the supersaturation distribution and becomes narrower like this, and so you get less water. But at the same time, if you increase the turbulent kinetic energy, that can increase the width of this and generate more. So this is intimately linked then to the cloud microphysics, this cloud fraction scheme, and we need to bear that in mind. So you might think that the evolution or the representation of your cloud is it's only as good as the things it's built on. So you can imagine all of this down here represents things like the cloud microphysics, the boundary layer scheme, and the cloud fraction scheme, and it's all been tuned together or as best they can to give you some representation of the clouds. But as soon as you make a difference to 1 bit, so here we've introduced a new cloud microphysics, say, it might change the way the model behaves overall. And so, because it's not plug and play, you need to consider changes to other schemes as well to make things better again, and hopefully even better than they were originally. So in order to get over the hurdles required to get any new scheme or changes even into the operational model, we need to go do these sorts of things at the very least, which is go through these test suites. So there's 2 test suites that RMEDs, that's our regional model evaluation group, have come up with. So there's one that's centered around Darwin in Australia, and it's 60 days with 2 runs per day. So there's 120 simulations with 1.5 kilometer resolution. And then we've also got the standard operational UKV domain here. So it's 1.5 kilometers in the middle, and then there's various stretched bits outside. And there's a case study suite, again, of 120 cases, but these are spread over a couple of years. And again, it's 1.5 kilometers in the central bit. So we'll look at results from at least partially from those. Just a boring slide to just sort of introduce what the things that we'll be showing. So some RA2 things, which is our current operational model. There's two different configurations: T for tropics, which uses a PC2, which is a prognostic cloud scheme, and our old Wilson and Ballard microphysics. I must say that Wilson and Ballard microphysics is just coming up to its silver jubilee. It's been active in the model for over 20 years now. And then there's RA2M, which is the Smith cloud fractions, very simple diagnostic cloud fraction scheme, and Wilson and Ballard. And then, but most of the things I'll be showing are just, I'll call it WB. So it's bimodal cloud fraction scheme with Wilson and Ballard. So here we just changed the cloud fraction scheme. Then we'll have bimodal cloud fraction scheme with KAZIM. So now we're changing the microphysics. And then you can see some differences if you, instead of using a fixed number of droplets for in-cloud values, you make use of aerosol fields to work out and activate them to work out what droplet numbers. So you can do that one as well. So let's start off with a tropical case, so around the Darwin domain, just a snapshot 24 hours into a simulation. There's the GPM microwave radar product here, just to give you the context. And then we've got the 2 KAZIMs on the bottom. So one is got a fixed droplet number for cloud droplet number, and the other one's got one based on an aerosol climatology. And then at the top, we've got our Wilson and Ballard, our old single moment representation of the cloud microphysics. And over here is actually this KAZIM, which is double microphysics, but then set up as single moment. So it's the same code as this, same computer code as this, but the same science configuration as this. So you can see it looks more similar to our old Wilson and Ballard, and these look more similar to each other. And so there's 2 things really to take from this. We'll zoom in and we'll look at this area here and these arcs out here, arcs of convection, on the next slide because it's a bit easier. And you can see that the KAZIM one has these more blue areas, lighter rain, whereas if you look at the single moment representations, it tends to just go from 0 very quickly to very high rain rates, with none of this lighter rain easing you into the high precipitation regions. And if you look at these arcs of convection out to the north over the sea as well, you can see that there's this white is very off scale, in fact, very intense convective precipitation, whereas KAZIM models have much less intense precipitation and more, again, of the lighter rain surrounding it. And so that's just one case, but if you look at all the 120 simulations that were done, you can generate a versus rain rate here and this is the histogram, so a normalized frequency. The black line on here is radar observations, radar rain rate. The blue and the pink are the KAZIMs, so either the fixed number or the one based on an aerosol amount. And then the orange and the green are our single moment representations of the cloud microphysics. So you can see straight away that out here, it's much higher frequency than the KAZIM ones or the observations suggest. And on here, this is just if you divide the models by the radar histogram, you get this. So one would be perfect. So you can see at these lighter rain rates, the pink and blue is closer to the radar. And again, at these higher rain rates, it's the same story. When you're getting to 30 millimeters per hour, the single moment cloud microphysics is representing 10 times the frequency that the radar suggests. And this also feeds through to the size of the features. So if you try to track features, and so here, and you measure its size, so convert the area into a circle, you can plot that a radius of those effective radius of those circles here, and as a function of, well, as number counted, so a histogram. And you can see the red and the green line out here, much bigger sizes, are the operational model and also the Wilson and Ballard. So those have got the same cloud microphysics, but they've got different cloud schemes. So you see in this case, the cloud scheme doesn't actually make any difference. The pink here, if you can see it coming through here, is the radar value, radar histogram, and the blue and the green, light blue and light green, are again from KAZIM. And there's some indication that if you got droplet numbers, different droplet numbers at least to the fixed one we've got here, then perhaps you can make a better approximation to the observations. So an indication of subsensitivity to that, and so maybe it's worth pursuing an operational role for having that link between the aerosols and droplet numbers. So this light rain has been observed before with double moment and single moment simulations or representations of the microphysics. So this paper here, they were simulating an idealized squall line case over the United States, and they see that the trailing lighter rain in the trailing anvil area is better represented in the double moment compared to the single moment. And they also see increased rain evaporation in the heavy convective leading part of the squall line. And so if you've got more rain evaporation going on there, you might expect much stronger cold pools to be developing over near the surface. And so we can look at that in the model. So back to that tropical storm case. So we got them again, two KAZIMs on the bottom and the two single moments on the top. This one on the left is boundary layer depth. Purple, the darker purple colours are thinner boundary layer depths, and that's where you're getting cold pools, at least over the ocean. And on the right is relative humidity at screen level. So again, darker blue colours are more moister regions. And so if you look over these ocean areas in terms of the KAZIM, you can see bigger blue circles where the cold pools are being generated, and you can see it in the boundary layer depth as well. But it's not so strong in the single moment compared to the double moment. So it looks like the cold pools generated from the double moment representations are more intense and stronger. And you can see that there seems to be some evidence of these cold pool effects being there. So this is just the worldview imagery from that day. If you zoom in on this bit here, you can see all these arcs of cloud that presumably forming around the convergence lines as these cold pools spread out. And to be a bit more quantitative, we can look in the model fields at so if we integrate the evaporation of rain rate up the whole column and then plot that against the rain so do the same with the rainwater. We integrate that up the column and then plot it bin-wise like this. We can see for the very high rainwater columns, so the deep convective regions, then the evaporation rate, so this orange and blue from KAZIM, is many more times 5 or more times greater than what's seen for our single moment representations. And so this is driving less intense precipitation compared to the single model simulations, and it's also driving the cold pore formation and formation of finer scale features and a different evolution of the cloud fields and eventually precipitation. And so you can see how that could be important for weather forecasting. So here's an example taken from Stu Webster's Southeast Asia real-time monitoring. So this is running at just over 4 kilometer grid resolution over this warm pool area. And you can see this is at nearly 4 days out, and KAZIM is predicting 2 cyclones spinning up here in the middle. But the standard model using the single moment microphysics is just about seeming to pick something up here. It's a bit flabby, but nothing, definitely nothing to the west of it. And if you look at the GPM for the validation time here, you can see that indeed there are 2 cyclones being picked out. So it's looking like, for this case at least, KAZIM was doing a better job in predicting these events out to 4 days, which would be quite useful. We can going back to Darwin itself. We can look at standard synoptic weather observations. So this is now looking at temperature, screen level temperature, screen level humidity, the cloud cover when you look up, and the wind at 10 meters. And the top row are just the bias, the mean error, and the bottom row the root mean squares. And blue and green are KAZIMs, and red is the single moment microphysics, the old microphysics. So you can see for temperature and humidity, the KAZIM's definitely doing better. For cloud cover, it looks like the different droplet number introduced by using aerosol is making a better job of the cloud cover. Wind is pretty much of a muchness. So in terms of synoptic behavior, it seems to be doing better as well generally compared to a single moment scheme. We can look in more detail at the radar. So these are CFADs. So these can these represent reflectivity, sort of 2D histograms of radar reflectivity versus altitude. And this is from the Seapole radar in Darwin. And you can see it's got a maximum of about 7 kilometers. And it's got basically a monotonic behavior away from that maximum in every direction. If we look at what our operational model looks like in this framework, you can see that it's not really got this maximum at 7 kilometers, and it isn't as this funny upturning maxima here. And there's also 5 kilometers is at the freezing level, so there's something funny going on there at the freezing level. If we go to this one, so now all we've done is change the cloud fraction scheme, because this Wilson and Ballard is in both of them. It's starting to generate a maximum here, which is nice, but it's still got a discontinuity, totally different behavior below the freezing level. And then if we go to the KAZIM, it's starting to look a bit more like the observations. It's still not as high frequencies here, and maybe that's because it's a bit too broad relative to these observations, so we need to be brought in, although that might be a radar sensitivity issue to be determined. But it seems to behave better below the freezing level as well. And also, this one's the one using the aerosol climatology, and this one's a fixed number, so you can see it makes a difference to the behavior of the cirrus at high levels. And you can see that more with the if we compare broadband outgoing long wave and short wave, so short wave on the left, so the black line with the shading is the observations, and the various color lines here are the different Wilson and Ballard, so our operational microphysics, and different KAZIM ones. So they look pretty much similar in the short wave. They're probably a bit too bright relative to observations, or show higher frequencies of brighter pixels relative to the observations. Long wave, there's the most differences. The green one, so Wilson Ballard's showing much too high cold cloud, but so's KAZIM with the fixed number. But conversely, the KAZIM using the droplet number derived from the aerosol is showing actually it's not got enough high cloud, and it's letting through energy from lower down. So it looks like it would be possible to probably tune our fixed number one to be closer to the blue one and follow that better, but that's for later work. And again, also you can see that if we take a cross section across the middle of the that case, this is our two KAZIMs. So our KAZIM with fixed number has this green, which is cloud. So it's green, which is the cloud ice. So it's got this thinner ice cloud at the top. Whereas our ARCL, the one that uses aerosol, because it's got lower droplet numbers being formed at this altitude, has got much less, or well, it doesn't even feature on this scale up here. Although there's some nice some nice evidence perhaps of around here it's about -5. So we have ice multiplication via Hallett-Mossop. So there's some little green bits in there which are probably secondary production occurring. So when you do these case studies, you can generate a scorecard. This is our typical scorecard that we generate with Ahmed suites, and they do comparisons against things like, as I was showing it before, the temperature, these screen level values, temperature, wind, 10 meters, cloud fraction when you're looking up, cloud-based visibility and precipitation. And the green means it's better than our operational, and the solid outline means it's significantly statistically significant as well. So that's doing a good job improving on our operational model. This is the change in the fractional skill score. So this is more of a measure perhaps of the shapes or the patterns of rainfall rates, and again that's showing green as well compared to the operational model. Now, just a quick few slides about the UK. So mid-latitudes. So operational meteorologists at the Met Office, the forecasters, they have a ticket system where they can list or identify deficiencies that occur for what they feel occur more than once, or common deficiencies in our model that we use for the operational weather. And so there's a number of tickets. So there's 10 that are deemed major or high deficiency, and they've all been open for 5 or more, three or more years. And they are things like the minimum temperatures are too high, and the maxima are too low. There's a lack of light rain and drizzle. So you can see where I'm going with that one. And there's unrealistic fragmentation of precipitation bands. Those two can be taken together really. And also things like excessive development of showers in terms of intensity and distribution. These are more like popcorn, really small things rather than deep events. So if we look at these, just an example that speaks to these ones about the unrealistic fragmentation of precipitation bands and lack of light rain, too much heavy rain. So this is our radar from that day. So you can see this blue, lighter blue rain with some green and yellow in here, covering large parts of the south east of England. In our operational at the time, it's still operational model, it's just the greens and yellows and hardly any of the blue, and it just occupies this southern central part of England. Whereas with the new KAZIM and Bimodal cloud fraction scheme, we get a better spread or coverage of the lighter rain, and it shows the frontal rain structure is more cohesive across its entire length, whereas it's more broken here. So that seems to solve some of those problems, or go some way to solving some of those problems. Another one was this extensive or excessive showers. So in the radar, there's nothing, I think, of these small showers, whereas the operational model was coming up with these pixel size, so only 1 or maybe 5 kilometer wide, or maybe a bit more than that, 5 kilometer wide showers are popping up, which in these pinks, these are very high rain rates just on pixel by pixel basis. And now with the new configuration, that's much more reduced. So hopefully that's also meeting that problem. And then in terms of the errors in the temperature, so this is just showing that bias in the temperature and the RMS. So the red is the operational model, and the pink and green are the KAZIM variants, and so they're showing that bias is now reduced compared to the operational, both in the early morning hours and in the afternoon. And finally, you can look at the scorecards for those, and it shows, relative to temperature, wind, cloud fraction, and so on, we're getting improvements across the board. The one fly in the ointment is compared to gauges, the precipitation seems to be a bit worse. But the fractional skill score, which looks at the patterns of precipitation against radar-derived rain rate, seems to show more impressive behavior. And we think, well, I think this to be decided or to be tested, is that some of this negativity is due to a very small positive offset bias we have of 0.02 millimeters per hour, which we hopefully can tune out in future. Okay, so that's our KAZIM microphysics, which is double moment and seems to do a better job across the board compared to the single moment one that's currently in the operational model. But by introducing double moment, we introduce many more degrees of freedom and more unknowns relating to all the extra process rates we're seeing. So on the left is just a simple box diagram from Wilson and Ballard with a few process rates linking all the boxes together, and on the right is actually from Seifert and Beheng, their scheme, their box model with all the bootlaces of different colors for all the different rates you need for number and mass. And so there's many more things that definitely need constraining, either in the laboratory or with aircraft or radar data. So things like all of the graup or hail, if you have it as well, process rates and representations. So this paper, they were looking at the sensitivity to changing graup density. And they're showing us a function these cross sections through the radar reflectivity. Through the radar reflectivity. So the top two show the changes to graup density. And maybe even more impressive is changes to graup drop collision in these bottom ones, where they're seeing much more extensive downwind ice anvil, because of those sensitivities. Other things are secondary production. There's no real. It's pretty unconstrained. We have few laboratory measurements. There are lots more laboratory investigations going on now. So at the moment in our KAZIM, we just have a representation of the old Hallett-Mossop Rime splintering, which happens, around -5, a couple of degrees either side of -5 degrees Celsius. But there are other things. So there's this paper here, Kainert et al. In Alexei Kiselev's group, where they've been looking at rain droplet shattering, basically, as they freeze. And so there's if you look at their paper, they have one example here where a droplet shatters into two, and this very microscopic little ice particle fires out, which could then be a seed for, well, at least it's generated a new ice particle which can go on to grow and form snow eventually. So there's all these other potential mechanisms as well, and we need to have more of these put into the model and their rates better constrained. Things like ice nucleation. So as I said, we can couple KAZIM to things like dust, so we can directly diagnose number concentration for ice from the aerosol species. This shows one example from this paper here, 3 different cases. This is the satellite outgoing shortwave, so the red is brighter. Our global model, 20 kilometers, is all blue, so it's not very bright, and it's mainly because it's removed or got rid of all of the liquid water. So in this case, with decreasing basically ice ice nucleating particle concentration, which leads to decreasing ice particle concentration, which in turn leads to an increase in the amount of water. You can see that it's getting redder and redder, or brighter and brighter, as we put more and more water back into the system. So there's ice nucleation to be constrained and tested. There's things like, so we're using double moment, which seems to give this clear improvement over the single moment representation in terms of how well it matches the radar rain rate or precipitation observations. But what about higher moments? Is it worth going to 3? And this paper here suggests that, this paper here suggests that even just going to 3 moments could give you something that's so it's the green 3M full here, could even match quite well a very expensive SBM as safe at Bimodal, I think, and so it does a very good job of representing that. So there could be room then for going even to 3 moment microphysics, at least for rain, where there could be observations to constrain it. There's also things like aggregation of so cold of snow, definitely, and ice, all of the ice species. The aggregation of those is very unknown. So there's some these very simple, using spheres, laboratory measurements 60 years ago, and then there's this one here that was done. I think it's the only other one I know of that was done using more realistic ice crystals in a big cloud chamber, but that's all we have. So and these can be very important to the evolution of the cloud aloft and how that impacts on things like the CFADs that we were looking at earlier, and then how that feeds through to the precipitation. Perhaps the biggest problem we have at the moment is this overlap of mixed phase. So in a grid box, even if you're a kilometer, if you have some fraction of the grid box which you say is liquid and some fraction which you say is ice, you have to decide what fraction of that grid box is where they're overlapped. And so we've got this thing called MPOF, which is mixed phase overlap factor. And so when it's half, so this is ice and this is liquid, then you say half of this is overlap with this, so about 0.1 or 0.1 exactly of the grid box is actually mixed phase. 0.4 is just liquid only, and 0.1 is just ice only, and that changes all the way down to 0 with when you set that to 0. Although that once you get the sum above 1, then you have to have some mixed phase. So there's no real physics, I don't think. I can't think of. I haven't seen any that tells us how this overlap should be, and you can think that maybe it should be different in convective regimes compared to stratiform regimes, but we have no way I've not seen any physics that try to describe that, and maybe the best way forward at the moment is to go empirically look at the distribution of these things. So I'll just get to the conclusions. So KAZIM is our new double moment microphysics that's been tested and now is accepted, I think, for our new regional configuration next. Hopefully, that's timetable to go operational next autumn, so 2023. And what I've hopefully showed you today is relative to the single moment microphysics, so our standard operational one. KAZIM shows us less of the intense precipitation and more of the lighter precipitation. In KAZIM, convective cell sizes are smaller, and also for we've seen that in the tropical, and then for the UK, we've seen that improved problems that our operational meteorologists, our forecasters, have been raising over the last 8 years or so. One thing I haven't shown anything really, but one other useful thing, both for developing and just to make things easier, is that KAZIM plus the bimodal cloud fraction scheme means that we don't have to have 2 configurations, one for mid latitudes and one for tropics. It seems to outperform a single combination of those with some boundary layer scheme outperforms any separate mid latitude or tropical configuration. And as I said, we've got more now. We've gone to double moment or more. We've got more degrees of freedom as to all these process rates that we need to constrain other parameters for, or things like the representation of size distributions or densities. Yes, and that's it. KAZIM is our new double moment microphysics that we'll be starting to use operationally from next year. So thank you, and I'll try to take any questions you have.
Thank you, Paul.
Hello.
Sachin or Mahim? Yeah.
I think there are no questions on YouTube at present. So
Can't hear you.
Yeah.
Yeah, right now Dr. Pandithure has raised his hand. Maybe let him speak.
Okay, thank you. Thank you, Paul, for the very informative lecture on cloud microphysics. So I just want to know, so you showed some different simulations, KAZIM and KAZIM aerosol climatology. So in aerosol climatology, you used climatological aerosols, but only in KAZIM, what kind of aerosols are prescribed?
So they are from classic climatology. So, you know, classic is just a single moment representation of aerosol that was used in HAD Gem 2 or something, and earlier, or earlier than that, which has been replaced by the new double moment aerosol in the global climate model. So all you get is a single moment climatology, and the way it works is all of the soluble species are added together and then converted into a number concentration, and then KAZIM tries to activate those. So when you base the droplet number on your aerosol, it's only going to be as good as the aerosol representation. So that was very simple. So it's more of a sensitivity to see if is there any sensitivity to having a different droplet number. And so yes, so it looks like there are some good aspects of doing that. So maybe we should pursue using a better aerosol representation and coupling that. Yes.
Oh, thank you, Paul.
Sachin, you have a question or?
Yeah, can I?
You are not audible.
I think some problem is there with mine. Can you hear me? Yeah, we could hear. Yes.
Hello.
Paul,
can you talk loud?
Yeah, can you hear me now?
Yeah.
Yeah. So in one of the
Simulations.
Oh, sorry. I will write the question here.
Okay. So is Sudarshan having a question also? We were trying to speak. Yeah.
Hello.
Yes. Let us address Sudarshan's question now.
Yeah. Hello,
Mahim.
Paul. Yeah.
Hello.
Actually, I have a few questions regarding your presentation. So first question is, what is the advantage of this two-moment scheme with respect to other existing two-moment scheme that are available in WRM model?
So one is that it's because we want to eventually use it in our global model. So it's been designed to couple directly to the aerosol representation in the global model, so which is a two-moment aerosol scheme. And the other thing is it works because it's unfortunately, or maybe not, in the things aren't plug and play, and because we have to it works in concert with the new bimodal cloud fraction scheme and the boundary layer scheme. So if we just put in another double moment scheme, we'd have to add things to make it work with the double moment aerosol scheme, and also the links into the cloud fraction scheme and things like that.
Okay. And my second question is there any parameterization for mixing in this scheme, like cloud environment mixing? Is there available in this scheme?
So that's handled more by the by the boundary layer scheme.
No, I'm talking about cloud environment mixing, like how mixing is represented in like homogeneous type of mixing or inhomogeneous, like it will affect the radiation properties of the cloud also, right?
Oh, do you mean how if you evaporate things, how does the droplet change?
Yes.
Yeah. So one way. So in terms of if you reduce the amount of cloud fraction, we reduce the the grid box mean number concentration, so that the droplet number is maintained. So that means, yeah, they're going to get smaller. Yeah.
Okay, and my third question is how aerosol perturbation will affect or impact the deep convective cloud in this microphysics. Is there any study available?
Sorry, say that again.
How aerosol perturbation will affect deep convective cloud physics in this scheme? So, is there any available study who is doing some investigation of aerosol indirect effect or something like that?
Yeah. So if you look at the third, Cali Furtado at the beginning, he's got some, or you can email me and I can send you some. So he's done some over China, where he's looked at if you increase the complexity of the aerosol interactions in a deep convection from just being, you look at the aerosol field and create a number concentration, all the way to you use up the aerosol and rain it out. So that's fully processing the aerosol. So you can deplete the aerosol. So he's got a paper that looks at the impacts of aerosol cloud interactions of different complexities on deep convection over continental China.
Okay.
Yes. So if you just email me, I can point you to those papers.
Sachin, we have some questions in the chat box.
Yeah, there are some questions in the chat box. Mahen, you please read it out.
Yeah, Dr. Jay Kumar for NCMR WF Delhi, he's asking, please put your comments on UKCA mode instead of, I think UKCA model instead of ARCL in KAZIM simulation. Can you please comment?
So I haven't done extensive tests. I get 100 cases against UKCA mode. That's what you're doing.
Yeah,
but
yeah,
but
please.
so it's I mean it does. It will be better than the aerosol climatology because that's fixed, whereas you've got emissions in UKCA mode. So the drawback of linking to aerosol is your cloud evolution then is going to fall back to how good your aerosol model is as well. So so hopefully UKCA mode aerosol as a basis to build KAZIM on will give you better results than ARCL.
Yeah, he has another question. How much improvement is expected in MCS in KAZIM with respect to WB, since cold pool is better in KAZIM?
So I haven't got any specific cases I've looked at, but it definitely looks statistically like it produces better structures. So when we've looked at cases over the UK, we can see more organisation of intense, thunderstorm regions compared to our old operational microphysics, which tends to break up the structure of any MCS. So it makes more organised rainfall events, convective events.
Yeah, thank you. Sachin, can you please put your question? Can you hear
me now?
Yeah, you can hear.
So, Paul, I have one question. In one of the slides, you compared, say, the effective radius with different simulations. And I noticed that there are some differences between the model and the radar derived safe radius. So, model overestimates the simulated safe radius. So, what would be the physical reason for that?
What did I compare? Sorry. Which
compared
one?
the sail effective radius observed by the radar and compared
radar.
it with different simulations.
Yeah, so that's. You mean this one?
No, no, a couple of slides back.
That one.
Sail effective radius. Sail effective. I think you have to go back.
I mean this. Okay, so this. Okay.
So you have a line plot.
Before
Yeah.
this.
Yeah, I got it.
Before this.
This one, yeah.
Yeah.
So okay, so just to be clear, this effective radius is like the geometric size of these features, yeah?
Sometime you mentioned that it is greater than 32 millimeter per hour.
Yeah, this. Yeah, so this. So this you make this graph by looking across these fields and looking for elements. So you identify all the features and then you find the ones that have some pixels in that are greater than 32 millimeters per hour. And then you look at how big they are and just plot the histogram of that. So this tends to find either because it just makes big regions like this, or it just generates higher precipitation values anyway, much bigger features compared at the same rain rate compared to the observations or the KAZIM models. So I'd because you don't see that in the single moment. So I described that to the impact of change in the cold behavior. And so the fact that because double moment seems to evaporate much more efficiently in the deep, thick rain columns than the single moment.
Okay, thank you.
Mahen, I have a couple of questions.
Yeah, please.
Or Sachin, are you finished or?
Yes.
Okay. So, Paul, very nice presentation. I was just wondering how this, you mentioned about double moment scheme was able to create the cold pools better. And is it so that the aerosol cloud interaction played a defining role for the precipitation, initial precipitation, and then the cold pool was indeed very correctly simulated, or how did you really come to such a conclusion?
So
I saw the radar observations you were showing, but that radar observations may show for a couple of events, right? But whether you have done any kind of several events and more statistics on these factors?
No, not yet really, because it takes it takes a while to run these. But so these two bottom ones, they're snapshots, but you can see in this one it does seem to look like there's a bit more more activity in the aerosol one rather than the one that's a fixed number. But when you look at the integrated
also. Towards
that
what I could see is for the heavy precipitation events, you could see the major difference, right?
Yeah. So that's just a single scene, so we'd have to do that over many just to see if it's robust behavior. But so it does. There are things where it does seem to have there are sensitivities to using aerosol instead. And as I said, if we just need a better representation of the aerosol to make it evolve better overall compared to just having a fixed number.
If I remember correctly, there was one paper from you and others on the in-cloud activation. I think there was a scheme that you put forth.
Yeah.
And is it something part of this KAZIM? Or?
Yep. So yeah, so that's Hamish Gordon did that, and that's part of this as well. So you look to see if there's already part of the cloud. So what's the new bit of cloud fraction and water that gets generated, and just do the activation there. Yeah.
Yeah, okay. And you also mentioned about, I'm just rushing through some of the questions. You mentioned about the process rate, constraining the process rates.
Yeah.
What will be the strategy for that?
So using things like the CFADs, have I got it here? I've gone past it. So things like this, if we change things like the aggregation, maybe we can bring this in, make it narrower, but it might make the whole thing shift that way. Then we have to do that, get that right at the same time as we get this right. So we know we have to change the droplet numbers to get in between these two somehow. That's one way to do it. But so the idea to constrain will either be using laboratory measurements that have been, so we'll put those in because they're observed, or we'll try to use these top-down things like the outgoing radiation or radar statistical examples like this to work out what provides the best overall improvement. And then using aircraft data as well is the other thing. We'll be looking at lots of aircraft campaigns to try and see if we can find a better set of numbers or process rates to match the observations.
And
so yeah,
is this bin schemes also?
Hello, Tara.
Bin microphysics also considered?
Not for this. There's the bin scheme. We have a bin scheme in a LES that KAZIM is also in, so we can compare there. We have no plans yet to introduce a bin scheme into the global model.
What I'm asking is to derive the process rates.
Oh yeah. So one way would be to try to use our LES where we've got both microphysics side by side to tune one to match the other. Yeah.
Okay.
But if you've got volunteers to do that as well, that's good.
Yeah, but I've seen that in ACP recently a number of very nice publications on secondary ice production and ice nucleation and all come up from your group, and really interesting studies. And yeah, that region is very much important for monsoon studies as well.
Yeah. So we definitely need because we need observations from all regimes, so all the tropical and we always have trouble with in the global model for the monsoon. So
yes,
it's I don't know whether that's probably nothing to do with microphysics, but as we go to higher resolution, we need to do that better anyway. People.
Do you think, one more question? You mentioned about the resolution also. Do you think we should run at close to 1-2 kilometer resolution for the weather forecast? Because it appears that these cold pools and all not resolve properly as you go to coarser resolutions.
What resolution you're running at the moment?
No, I think currently our forecast at 12 kilometer resolution.
Okay, that's quite, I guess that's quite big. So, but what you tend to find is, as you go to, I don't know about 12, but as you go to like 4 kilometers, you still see cold pools, but everything becomes aliased onto bigger scales.
The boundaries may not be well defined, and their propagations may not be well captured by the model.
Yeah,
looks like it. I think there are more questions from Sachin or.
No, Sachin, he has asked.
I asked.
Yeah, there are no more questions. Yeah, I think Dr. Paul is hungry.
Yeah. And Mahen, you have any question or?
Yeah, I know you're hungry, but still, I was thinking. I was just
That's
wondering.
okay. Yeah, yeah.
Yeah, I was wondering when you describe about the shape parameter in the drop size distribution. So, do you fix with some observations, or you assume some mu values in your model? Just wondering.
Yes, some are fixed to observations, but some are being just set pragmatically because they make things like this behavior. It changes. It can change that. So, and some are just being set to what's previously been set for different microphysics representations. But ideally, yeah, we should have them set to observe values. I mean, but some things like rain, it looks like it might be even better just to have some kind of shape or dispersion parameter that's a function of rain rate. So those are more things to be discovered, because if we make changes like that, then we need to run all these 250 cases again to make sure it's still stable, because if one fails, we have to go back again.
Yeah, thank you. There are no more questions, I think. Yeah.
Yeah. Then let us thank Paul profusely for his time giving this lecture, and we are very happy to have this lecture, and I hope everyone will see it and learn more from you. Thank you so much, Paul.
Thank you very much for inviting me.
Yeah,
Thank you,
Paul.
Thank you.
Thank you. Bye.
Thank you, Mahen and Sachin and everyone who participated in the
Yeah.
asking questions.
Thank you.
Thank you. Bye bye.